properties of solutions. So in this first video, we'll be doing approximately the first 3 sections of this chapter, where we'll talk about concepts of solution composition, some thermochemistry stuff, including some enthalpies and energies of solution formation, and factors that affect a solubility. So this may be a little bit of 152 review, but we're going to start with just kind of some concepts of what is a solution. So most commonly we think of solutions as either a liquid and liquid mixing together, or a liquid and a solid mixing together. But really, when we're talking about solutions, we could have gases, we could have solids, and we could have liquids be a part of that. So for example, we could be talking about the solution or the mixture called brass. Brass is a solid solution, and the state of both the solvent and the solute are both solids as well. Carbonated water is a really good example of a liquid solution that has a solute that is a gas and a solvent that's a liquid. So it's important that we kind of expand our concept of what a solution is. To be able to determine kind of how concentrated a solution is, we use the concept of molarity. Molarity, we use a big M for it, and it stands for moles of solute over liters of solution. We also use the concept of weight percent, mole fraction, and molality. So you will have to be able, and you'll have opportunities in your homework to practice with all of these different kinds of solution composition equations. So this first word problem gives you an opportunity to go through and use those different kind of composition equations. So you can go through and practice using it for molarity, mass percent, mole fraction, as well as molality. Now remember, for molality, we have to have kilograms of our solvent. So make sure that you are converting not only to grams, but then going through and doing your kilograms of that. Here's your first door question for chapter 11. One last type of equation that we use to kind of deal with quantities of solutions and their composition would be normality. And this is kind of done in equivalence. So an example that we have here is to calculate mass percent, molality, and normality of this sulfuric system, or sulfuric acid system. So to be able to do it, we first need our density and our mass, and from that we can go ahead and start calculating our answer. And then lastly, to do the normality, since we'll be able to figure out that sulfuric acid can donate 2 protons, right, because it's H2SO4, so both of these are acidic hydrogens, we can get 2 equivalents of it. So go ahead and answer this question. Next, we want to talk about really how does a solution form. So we've all seen examples of solutions form, even something as simple as salt water. NaCl dissolved or dissociating in water breaks apart and makes a new solution. However, we need to kind of discuss what's really happening at a molecular level with this. And really this comes down to concepts of molecular forces. And so we need to go through and kind of logically break down the different steps that are occurring and think of them in their kind of thermochemistry environments. Steps 1 and 2 would be an endothermic process, because we're going to have to overcome our solute and solvent, which were stable. We're breaking them apart. So those would be endothermic processes. And step 3 is oftentimes an exothermic process. So when we're dealing with the enthalpy of a solution, we're going to have the enthalpy, or the entire solution's enthalpy will be the sum of all the H values making up those different steps. The enthalpy can have a positive sign when energy is absorbed and a negative sign when it's released, just like we've always done. So these are very, very important visual graphics. I would strongly encourage you to be able to know how to draw these, know and understand what is happening in them, where if maybe on a test or a quiz you saw an energy diagram like this, that you would be able to explain what's happening in each step, what each delta H means, as well as give an example of a type of solution in which this would occur. So I'd strongly encourage you to be comfortable with the images on this slide. So again, when we're looking at the types of solutes and solvents that we have, obviously this kind of is breaking it down into a little more of a logical thing, but it all comes back to this same general equation that we have here. Right? If we have a nonpolar solute and a polar solvent, we know that like dissolves like, and these are not like to each other. So we would have a small delta H for part of it and large delta H for another part of it, and for the third step it would be small, which means the overall would be large and positive, no solution forms. So make sure you're comfortable with the logic of how we went through each of these steps as well. I'm just putting this up as something that you will see as you move through your chemistry career, especially if you go on to organic chemistry. This concept of thin layer chromatography is a good analytic tool often used to take advantage of capillary action in solvents. And so what will end up happening is you'll have a silica plate and you'll put a little tiny spot of your material that you want to analyze on your silica plate, and you'll let that sit in a little well of solvent. And you can play with different polarities of your solvents, but over time capillary action, like a wick, would suck the solvent from the bottom up to the top. And as that happens, whatever material was in this spot that you put here will travel with the polar solvent. The less polar material in that mixture of that purple dot will be lower because it's not as polar. More polar. It needs more polarity to pull it up farther. The less polar solvents will travel further. Here's your second door question. Now, when we're looking at the properties of a solvent, we kind of have to start thinking about things like their intramolecular forces and how that's going to relate. We also need to talk about things like polarity of our compounds. So all the things we talked about with Lewis structures and understanding the concept of polar bonds and polar molecules still plays a role here. For each of the following pairs, predict which would be more soluble in water. So if we have these two compounds here, which one would be more soluble in water? The NH3. If we have these two compounds here, again, I know it's kind of hard to visualize it in the space-filling model, but by the Lewis structures, you should be able to determine which one is the better choice. In this case, the CH3COOH is a better choice than the CH3COOCH3. Go ahead and answer this question. The effects of the structure of a molecule are really important to its solubility. So we've talked about this before in terms of, the Lewis structure with polarities, hydrogen bonding, dipole-dipole interactions. These intermolecular forces cause molecules to react differently with water or different solvents. So a very popular way we describe this is using vitamins. There are two kinds of vitamins. There are water-soluble vitamins and fat-soluble vitamins. Fat-soluble vitamins are going to be the nonpolar ones. Fats are nonpolar as well, so that's why they're soluble in them. Think about the last time you cooked dinner. Maybe you cooked some meat in a pan. The grease, the fat from the meat won't wash away with just water. You need soap in there as well. Water-soluble vitamins would be things like vitamin B, vitamin C, and so this is very helpful. We know that fat-soluble vitamins can actually be dangerous to you if you take too much of them. What ends up happening is, unlike a water-soluble vitamin, your body can only process and handle so much of a vitamin at a time. Once it has the amount it needs, any extra you take it can't be used. So if it's a water-soluble vitamin, oftentimes what will end up happening is you will excrete it. So oftentimes, if it's water-soluble, that means you're going to pee it out. So if you drink 5,000 times the amount of vitamin C that you need, you will just pee out the extra vitamin C. Same with vitamin B. So if you've ever taken a vitamin B complex before, oftentimes you will notice that the urine after taking a vitamin B complex will be bright, bright, bright yellow, and that's actually the excretion of the extra vitamin B. What's dangerous with fat-soluble vitamins is once you've taken the maximum amount that your body can absorb at that time, your body can't excrete it. We can't pee it out. So what ends up happening is your body says, okay, we'll store this for later, and it gets stored in fatty tissue. And so you can actually build up dangerous levels of these vitamins in your body because you can't excrete them. Another concept or another factor that affects solubility is the pressure on the system. So especially if we're talking about a solution with a gas. So if you want to think about something like carbonated water, where the gas is the solute and the solvent is the water. Obviously, the pressure that gas is experiencing is going to play an important role in how soluble it is. So we're going to be talking a little bit about the concept of Henry's law, and obviously the increase of pressure on a system will increase the solubility of the gas in the system. We know gases, if we increase the pressure that the gas is experiencing, more of it will be soluble in the solution than less. This is the classic example of what happens when you leave a soda can open to the exposed air, right? So the gases of the carbon dioxide in the soda can are under less pressure in an open situation than they are in a closed. So this is a really good practice problem for this, right? Like we said, a certain soft drink. So a soda bottle is opened at 25 degrees Celsius and contains carbon dioxide gas at a pressure of 5 atmospheres. So again, going through, once the bottle is opened, we've lowered that pressure. So what is the new solubility? So we can go through and determine that for Henry's law, that the K of the carbon dioxide would be 3.02 times 10 to the negative 2 moles per liter atmosphere. And in the unopened bottle, the pressure is 5 atmospheres, right? So then the new C for the CO2 would be 0.16 moles per liter. And then we can do the same thing for the open bottle, and we can compare them. So we see that we get 1.2 times 10 to the negative 5 moles per liter in the unopened bottle, or excuse me, the opened bottle. So there's a huge change between that 0.12, the 0.16 in our closed situation, right? This is the closed bottle, and our opened bottle. Obviously, we have to keep in mind that this is 10 to the negative 5, right? So because of this, when we have the bottle opened, the gas will escape, and this is why soda goes flat. Just like we know with all of our gas behaviors, temperature is also something that affects gases and their solubility, but we'll also see this in solids as well. Solids and gases will have an inverse solubility effect with temperature. So solids will dissolve more rapidly at higher temperatures. Gases will be less soluble at higher temperatures in liquids. For solids, the good example is when you have a hot cup of coffee and you add sugar to your coffee, the sugar dissolves very readily in a hot cup of coffee. If you have an iced coffee, your sugar sits at the bottom. So we know that the solubility you've experienced, the fact that solids dissolve more rapidly in higher temperatures than they do in colder temperatures. solubilities of gases follow pretty much an opposite trend. Gases are more soluble in colder temperatures than they are in hotter temperatures. This is one of the biggest concerns with the rise in sea level temperatures. One of the important gases that is soluble in water is oxygen. So as sea water temperatures rise, the solubility of oxygen in that water decreases. So we have less oxygen dissolved in the water, which becomes a problem for things like living sea creatures. They still need oxygen, they just filter it through their gills. And so if there's less concentration of oxygen in the water, we tend to get dead spots in the water. Oops, sorry about that. The question is there. So again, this was ranking these in increasing solubilities. So you can look through these. And then which statement below is more accurately describes the effect of increasing temperature on solubility. Make sure that you read this properly. Right, dissolving a solid occurs more rapidly, but gases, as we increase the temperature, will decrease in solubility. So this ends our first video for Chapter 11. Make sure you're doing your reading as well as taking notes and coming to office hours and doing your homework.